Good day, everyone. So we're going to go over section 12.1, hypothesis testing. This is also known as significance test, but I'm going to use the word hypothesis, phrase hypothesis testing from now on. And what's going on here is that a researcher has a hypothesis. And once a researcher has a hypothesis, what naturally occurs is an opposing hypothesis just sort of naturally happens. Okay, so you have these two opposing hypotheses. You have the researchers, and then you have the opposite of the researcher's hypothesis. And in order to prove the researcher's hypothesis to be true, he or she needs to disprove the opposite hypothesis. And you see this in math, you see this in science, you see this even in philosophy sometimes. You disprove the opposite to show the other side is true. Okay? So based upon a random sample, if the researcher is able to disprove the opposite hypothesis, it probably shows that the researcher's hypothesis is correct. I say probably because we only took a random sample. We'll expand on this idea later on when we talk about type 1 and type 2 errors, but that's after we talk about hypothesis testing in detail, all right? So a hypothesis test has 5 steps from an academic standpoint. I say academic standpoint because if you're a researcher, you would have another step or two in here. For example, the first step is always state the hypotheses, okay? Now, if you were doing this for real, this is where you would collect your data. But we're already going to assume that the data has been collected and summarized. And it's going to be summarized and given to you in the problem, okay? So here, after we state the hypotheses and assuming that the data has been collected and summarized, we would go ahead and confirm conditions or state assumptions if we had any. 3, we would calculate what's called a test statistic. 4, we would go ahead and calculate what's called a probability value or a p-value. And then 5, we would say, are the results significantly significant or not? Then state the conclusion in terms of the problem. So those are your 5 basic steps. So we'll go through all 5 steps in detail. All right. So the first thing, a hypothesis is a statement about a population. All right. So such as the population proportion, right? Population proportion falls in a certain range of values, such as p is greater than 30%. So you would test if p hat was greater than 30%. Right? You would test if p, the population proportion, is greater than 30%, or you would test if mu was less than, say, 9. All right? So each hypothesis test has 2 hypotheses, like I was saying. So let's name them. We have the null hypothesis. The null hypothesis is a statement that the parameter takes on a particular value. Then we have the alternative hypothesis. The alternative states that the parameter falls in some alternative range of values versus the null. So let's start with the null. The null hypothesis usually represents the opposite of the researcher's hypothesis. That's usually the opposite of the researcher's hypothesis. The symbol that we use universally for the null is H0. H for hypothesis, 0. In math, that means null, empty. It's kind of like the empty hypothesis. For now, it's going to be written like this: H0 with that's a colon. Okay, it's not an equal to sign. Some sort of parameter is equal to some value. So, for example, you might write it as mu is equal to 10. How about the alternative hypothesis? The alternative usually represents an effect of some type. That's why it's usually the researcher's hypothesis. It's testing for some sort of effect. This is usually where the researcher's hypothesis goes, right? And there's 2 symbols that you could possibly use. We're going to use H sub A for this course because that's what the book uses. But if you ever see H sub 1 in another course, okay, they're talking about the alternative hypothesis. For now, the alternative hypothesis will be written. You got the same parameters as you saw in the null, but either you're going to write a greater than, less than, or not equal to sign to some versus some value. That value that you see there is the same value that you see in the null. So for instance, you might write the alternative is mu is greater than 10. So based upon the problem, we have to write out both the null and the alternative hypotheses. We'll practice this on the next slide, okay? It's important that we practice it. And like I said before, the hypothesis should be stated before viewing or analyzing the data, okay? So in real terms, in a real life hypothesis test, the researcher goes ahead and formulates a hypothesis and then collects the data, not the opposite. We don't look at the data first and say, okay, well, let's formulate a hypothesis from that. No, we formulate the hypothesis first and then we collect our data. Okay, so example one, a researcher believes that the mean temperature of all healthy humans is less than 98.6 degrees Fahrenheit. And so this statement right here would be like one statement in about 3 or 4 sentences, okay? And that 3 or 4 sentences is the problem that you would receive in WebAssign or maybe on the exam or something, okay? And so we have to pick out that one sentence that tells us, okay, what's the null, what's the alternative? This statement tells us that. And so usually when we write out the null and the alternative, the null is written first, then the alternative. Why do we do that? I don't know. Whoever started doing hypothesis testing, they decided to write the null first, okay? However, since the alternative is the researcher's hypothesis, it might be easier to start with it first since it is most likely to be stated correctly in the problem. Okay, so notice here that the researcher believes that the mean temperature of all, and so the mean of all, mean of a population, okay, is less than 98.6 degrees Fahrenheit. That seems to me that since we're talking about the mean, we're talking about of an entire population, we're talking about mu, is less than 98.6 degrees. So the alternative would be mu is less than 98.6. And what is the null going to be? Mu is equal to 98.6. The null hypothesis always gets the equal to sign. That's it. Okay. Now we're going to use this bit of information later on when we talk about p-values. Because the alternative has a less than sign, the test is called a left-tailed or a lower-tailed test. So less than sign means left-tailed, or if you will, lower-tailed. And we're going to use that bit of information when we calculate a p-value, so that's important to note that. Example 2. A newspaper editor believes that a particular candidate will receive more than 45% of the vote. All right, so we changed over to a percentage here because the underlying variable here is categorical. Who's a person going to vote for? In this one, it was temperature of a healthy human was the underlying variable. That's quantitative, plus mean. Thus we're looking at means here. Okay, here proportions. All right, more than 45% of all the votes. That sounds like to me the alternative would be P is greater than 45%. You could also write it as a decimal, and that's fine. So either way, 45% or 0.45. The null would be P is equal to 45% or P is equal to 0.45, either one. Because the alternative has a greater than sign, this is what we call a right tail test or an upper tail test. So greater than means a right-tailed or an upper tail test. And just as a note, if HA has either a less than or greater than sign, both of these are considered a one-tailed test. How about the third one? A professor believes that the mean time all college students spend studying per week has changed from 20 years ago when it was 10 hours. Has changed. Well, has changed. Does that mean less than? Does that mean greater than? Or does that mean either or? Sounds like either or to me. Has changed. We care that it is either greater than or less than. And so the way that we write that in mathematics is not equal to. So we would say mu, mean, right? Mu is not equal to the 10 hours, right? 10. What would be the null hypothesis? Mu is equal to 10. So anytime you see in the problem has changed, is different, not equal, okay? we're talking about not equal to sign here, because we're talking about either greater than or less than. So because the alternative has a not equal to sign, this is called a two-tailed test. And what we're doing here is that we are testing both greater than and less than at exactly the same time. That's just our way of saying, instead of saying less than or greater than, okay, instead of writing that all out to us, that just means not equal to. But we are testing both at the same time. And this would be a two-tailed test. So we'll shelve that information until we are about to calculate the p-value, but we won't probably calculate the p-value for a little bit. We're going to talk about the p-value, but calculating it is a little bit down the road. All right, so a test statistic describes how far the point estimate, so remember what a point estimate is, that's the value of the statistic, falls from the parameter value of the null hypothesis. All right, so a test stat, all it is, tells us how far away our statistic is from the value of the null. That's it. Okay. For now, this will be in terms of the number of standard errors between the two. I say for now because as we get into more sophisticated hypothesis testing, um, we may not measure things in terms of standard errors. Okay. We've been talking about standard errors, standard deviations for a while. Okay. And certainly that's going to apply here in the next couple of sections. But when you get into some more sophisticated, excuse me, hypothesis testing and statistics, not everything is going to be in terms of standard errors, okay? But I can guarantee you that the test stat is telling us how far away basically our point estimate, our value of the statistic is away from the value in the null. Okay, this is important. If the sample statistic falls far from the value in the null hypothesis, the test statistic will be large in magnitude. And so what I mean by magnitude, I don't care if it's a negative or a positive, okay? Just large in magnitude. So if the statistic falls far from the value in the null, the test stat will be large, okay? In terms of the number of standard errors in the direction specified by the hypothesis, specified by the alternative, is evidence against the null and in favor of the alternative. Now that's a mouthful, and you might want to read that a couple of times. But I think the best way to describe this is just simply with an example. Let's say that we were testing the following, that we have the null hypothesis set at p is equal to 30%. The alternative is p is greater than 30%. And we get a sample statistic, p hat, of 80%. Wow. So notice, pretty far away, right? And let's say that when we go ahead and I'll show you how to calculate a test stat another day or another time. But for right now, let's say the test stat turns out to be 7.5. Now, everything that you know about statistics, remember this is the number of standard errors away. Everything that you know about statistics, should anything really be 7.5 standard errors away from one another? No, heck no, right? That's really far away, okay? And so since 7.5 is really large for a test statistic, that's what it is here, okay? And because greater than 2, you're kind of getting far away in terms of standard errors. Well, greater than 3 is really far away, and 7.5 is really, 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 really far away, okay? That's telling us that probably then that since this is so far away from the value in the null, that this is probably not the value for p. That p has to be closer to p hat, okay? And it has to be what then? It can't be at 30%, it's got to be closer, right? And that means it has to be what, greater than 30%. That's all we're talking about here. Let's flip it around. Let's say that we were testing p is equal to 90% versus p is less than 90%. Let's say p hat turns out to be 40% in that situation, and the test stat turns out to be a negative 5.5. Well, negative 5.5 is really large for a test stat here because a -2 is getting to be kind of far away in terms of standard errors. And certainly less than a -3 is really far away. And so a -5.5 is really, really, really far away. And so since we got a p-hat that was really far away from 90%, probably 90% could not be the value for p. It has to be what? Less than 90%. Okay? So that's what we're talking about here. But they got to be far away. They can't be really close. Okay? Meaning p-hat and p can't be really close. Notice they were pretty far away. Okay? So we're going to go over that idea here in a little bit. So using the value of the test statistic, we then calculate the probability of getting that particular value, or more rare than it, assuming the null is true. We call this the probability value, and we shorten it to p-value, and some computers actually just write big capital P. Okay, don't confuse this with the population proportion P. Okay, these are not the same thing. The computer just shortened it to P because it has limited space. But really what we're calling it is the p-value for the most part, but really it's the probability value. So a lot of students get confused over, well, what are we saying when we assume the null is true? I think most people can understand the statement here, all right? But they get a little confused when they see assuming the null is true. What are we talking about here? Well, I think the best way to describe this is with a picture. So let's assume that this is a sampling distribution of a statistic such as p-hat, okay? So this is the sampling distribution of p-hat. These are all the different p-hats that we can possibly get. What did we find out is the center of the sampling distribution of p-hat? We know that the population proportion p, the parameter, is stuck right smack dab in the middle of that thing, okay? And so what we're doing in order to test the null hypothesis, okay? Remember, we test that guy, and if we could disprove this, that tells us something about the alternative then. Let's say that we go back to our example where we had p is equal to 30% here, okay? So what we do is we temporarily assume that that's true. And so we have a value for the population proportion p. So if we temporarily assume that that's true, what we're going to do is we're going to set 30% smack dab right in the middle of that sampling distribution. Okay, and then we go ahead and calculate our p-hat. Maybe our p-hat turned out to be right here. Now that's a little different than the example that I gave before, because before I said our p-hat was like 7.5 standard errors away. This is maybe what? Maybe about 1 standard error away. Okay, so certainly we can run into this situation. Okay, notice here that the p-value then would be, oh, this distance right here, and you're going to find out that this is a fairly large p-value in this situation. Okay, but if we had a p-value, if we had a sample proportion way out here, 7 standard errors, 7.5 standard errors away, what you're going to find out is that in this situation, see the sampling distribution actually extends out way out to here then, okay? In this situation, our p-value would be this small little area right there, okay? And that's what we're going to find out, is that the larger the p-value magnitude, the smaller, so let me say that again. The larger the test statistic is in magnitude, the smaller the p-value will probably be. And the smaller the test stat, the larger the p-value. So we're going to find that out here, okay, as we work through this. So notice I drew the sampling distribution as a normal distribution, and y central limit there and stuff, okay? 2, we temporarily assume that the value for p in the null hypothesis is the correct value, temporarily, right? An assumption can be overturned, okay, based upon sample information, all right? So we temporarily assume that the value for p in the null hypothesis is the correct value for the population proportion. And we place that value right in the middle of the sampling distribution of p-hat because we know that the value of p is located there. The true value would be located right there. So we have an assumption for it. Okay, fine. Throw that in the middle of the sampling distribution of p hat. We take a random sample and calculate the corresponding sample statistic. In this case, p hat, right? And then we calculate how far away p hat is away from the value of the null. That's the test statistic. So we need to calculate the number of standard errors p hat is from the value in the null. Maybe in our example, maybe an example that the book that this guy right here is, okay, notice p hat is pretty close to the value in the null. So maybe p hat was less than 1 standard error away, or right around 1 standard error away. So we got to figure out what to do with, when p hat is really far away from p, okay, from the value in the null, or when it's really close. Okay, so let's say that the p hat turned out to be 0.46 in that situation. Okay, please read this a couple of times. Okay, read this one a couple of times. Just because p hat is greater than the value in the null, you can't just simply assume that the true value of the population portion p is greater than the value in the null. I'll explain why, okay? But don't just make that assumption, okay? Because you have to understand that p hat can vary from sample to sample, and you got to take into consideration normal sampling error, sampling variation, all right? You got to take that into consideration, right? So hopefully my demonstration will show you this. So we got 0.45 in the middle here, okay? And let's say the standard error, and I'll show you how to calculate the standard error later on. But let's say the standard error was 0.05. And so if you go out to standard errors, these would be reasonable values that you could get for p hat then if p was equal to 0.45. Okay, so if the standard error was 0.05, you go out 2 standard errors in both directions. These are reasonable values in orange that you could get for p hat. You could get something that is a little bit less than or a little bit greater than. Okay, so the question then is, what are the values of p hat that would start to convince us that p is actually greater than 0.45? Well, if p hat turned out to be 0.46, that's not very, very convincing evidence that p is actually greater than 0.45. Why? Because p could certainly be equal to 0.45. Actually, it could be less than 2 if you think about it. Okay, let's not get too deep into this. All right, so what are the values that would convince us that p is greater than 0.45? Well, it would have to be stuff probably way out there, right? Okay, it would have to be stuff way out there. So in other words, p hat has to be more than a few standard errors greater than the value of the null to conclude an alternative that has a greater than sign. So if the alternative had p is greater than 0.45, we would need not something just barely greater than 0.45. We would need something pretty far away, because we have to account for normal sampling error, because we know that p hat varies from sample to sample, and it could be less than 0.45, it could be greater than 0.45, okay? If it was just barely greater than 0.45, well, is that overwhelming evidence that says, would you bet, how's this, would you bet $10 million that p is greater than 0.45 if our p hat was just 1 standard error away from it? No, you would have to have convincing evidence, right? Okay, and what's convincing evidence to a statistician? Maybe more than 2 standard errors away. We'll get more specific about that later on, okay? What about the opposite way? What values of p hat would start to convince us that p is less than 0.45? So let's change it around. Let's say instead of having in the alternative greater than, we had less than. So the alternative has a less than sign in it, okay? So we were testing if p was less than 45% of 0.45. What would convince us of that? Well, that's an ugly HA, isn't it? There we go. There's supposed to be a colon there. Okay, so let's say that we were testing that. What would it be? Something like 0.449? No, you wouldn't bet a whole lot of money on that one, right? Because of normal sampling error. We would have to be kind of convinced of this, and so we need p hat to be what, more than 2 standard errors away from the value in the null hypothesis to start to convince us that, yeah, p is less than 0.45. Okay, now we've accounted for normal sampling error. Okay, it's not probably based upon that. It's based upon something else. What is that something else? Is that probably the assumption in the null is wrong. So in other words, p hat has to be more than a few standard errors less than the value in the null to conclude an alternative that has a less than sign, or for that matter, maybe two-tailed. Because remember, we're testing both less than and greater than with not equal to. Okay, so you got to have overwhelming evidence, and overwhelming evidence here is be more than a couple of standard errors away. So this can all be confusing, especially when you aren't using standard errors in other hypothesis testing. And so what we do is that we change everything into a probability. That's where the p-value comes in. So the probability value, aka p-value, all right? P-value is a conditional probability. Remember talking about conditional probabilities? Probability of A given B, okay? So the p-value is the probability of getting the value of a sample statistic, or more rare than it, given the value and the parameter for the parameter the null is true. All right. So given that the null is true, that's this part right here. What's the probability of getting a p hat or a sample statistic? That we did. Okay. That's what the p-value is. So it is a probability. So never, ever, ever state a p-value as negative or greater than 1, because it is a probability. Okay, if you we'll have to calculate some p-values later on. If you calculate a p-value that's really large, greater than 1, you did something wrong. If it's negative, you did something wrong. It is a probability. It is a conditional probability. Okay, so let's say that, let's go back to the example. Our random sample produced a p hat of 0.46. What's the probability of getting this or something more rare than that, given that p is really 0.45? That would be the p-value in that situation. And what do you think? Do you think we would get a really small p-value in terms of probability, or kind of a little bit larger? Well, um, we're going to, if you answer the question, do you think that we would get a really small p-value? No. Okay. So if our random sample produces a statistic close to the value in the null, not many standard errors away, this will produce a higher p-value. That's the idea here that I'm trying to get at. Okay, let's switch this around. Okay, let's say that our p hat turned out to be in the blue over there. Okay, so if our random sample produces a statistic far away from the value in the null, meaning it's more than a couple of standard errors away, this will produce a low p-value. For example, if we assume that p was equal to 0.45 and we get a p hat of 0.59, this is rather unlikely, okay, to be that far away from one another. In this case, we think something is wrong with the assumption, meaning we think that what's in the null is wrong and what's in the alternative is correct. Okay. So how do we calculate a p-value? Well, it depends on 3 things. It depends on the shape of the sampling distribution. Okay. So what probability distribution is the sampling distribution taking on? 2, the value of the test statistic. So how far the statistic is from the value in the null. And 3, it also depends if the test is left, right, or two-tailed. So it depends on those 3 things. I give this 5 stars because if you use statistics, if you use stats in another class, they're going to expect you to know this. And I expect you to know this. The smaller the p-value, the stronger the evidence the data provides against the null. Meaning we're probably going to reject what's in the null hypothesis here, and we are going to say we like what's in the alternative. We accept what's in the alternative. So that is, a small p-value indicates to reject the null. We think the statement in the null is correct, and if we think the null is incorrect, that means we think the alternative, the researcher's hypothesis, is correct. Small p-value means large test stat. That means p hat was very far away from the null hypothesis. How small does the p-value have to be in order to reject the null? That's usually the next question students have. Okay, so if the small p-value means to reject the null, how small does the p-value have to be? Well, in the problem, there's going to be what's stated, there's going to be a number that's going to be stated. It's called the significance level. It's going to be stated right in the problem, okay? The symbol that we use for the significance level is alpha, okay? So the Greek letter alpha, lowercase alpha. And you can kind of think of this as our cutoff, okay? Because you said, how small does the p-value have to be in order to reject the null? Well, this is the cutoff. Okay, usual values for the significance level would be 0.1, 0.05, and 0.01. Most common value in practice is 0.05. And here's also gets 5 stars. You have to know this, okay? If the p-value is less than or equal to alpha, meaning it's really, really small, you go ahead and reject the null. That's what we mean by making a decision, okay, is rejecting the null, okay? So if the p-value is less than or equal to alpha, we reject the null hypothesis. So for example, if the p-value was 0.023 and alpha was set to 0.05 or 5%, oh, I see p-value is less than alpha, reject the null. That's small enough. Okay? What about the opposite? What about if the p-value is greater than alpha? We would say do not reject the null hypothesis. Okay, and that would be our decision. So notice that basically this is our way of saying we have inconclusive evidence. We don't know. Okay, this is our way of saying we don't know. So what exactly does this mean? Basically, all possibilities are still reasonable. Okay, so for example, let's say that this is what we were testing, and assume that we concluded do not reject the null hypothesis. Be careful. Watch what I'm saying here. This literally means that the population proportion P could be equal to 0.45. It could also mean that it's less than 0.45. It also can mean that there's supposed to be a decimal point right there. P is greater than 0.45. All of these are still in play. All of these are still in play. Okay? We don't know which one it is. Okay. Let's summarize. If the p-value is less than or equal to alpha, we would say reject the null hypothesis. So what that means is that we're relatively sure what's going on. We think that the alternative hypothesis is probably correct. And you can go ahead and literally say, go ahead and accept the alternative in that situation. Since we took a random sample, though, we are not 100% certain, but we are extremely sure of our final conclusion. All right? And the random sample produced statistically significant results. Okay, so when you reject the null, we like what's in the alternative, and we have statistically significant results. If the p-value is greater than alpha, we're going to say do not reject the null. Now pay attention to this. Pay attention. We are unsure what's going on, and basically every scenario is still plausible, like I was saying before. The random sample produced statistically insignificant results. And please pay attention to this. This does not mean to accept the null hypothesis. You never, ever, 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 ever accept the null hypothesis as being true. Okay, after the hypothesis test is run. You do not accept the null hypothesis. We're going to have a discussion regards to this later on, okay? But it's certainly well noted here. Do not accept the null hypothesis, okay? You're either going to reject it or do not reject it. You might say to yourself, hold on, Doug, do not reject the null accepting the null sounds awfully similar. Well, there's an extreme difference between the two. Okay, there's a big difference between the two. So do not say to accept the null. We're going to say do not reject the null. Okay, and we'll discuss why that is the case later on. All right, thank you for your time.